Alright folks, so in this video what we're going to do is we're going to take a look at a second problem, and hopefully due to the knowledge that you hopefully gained working through the last problem or seeing it worked through, you can try to attempt to solve a similar problem on your own. So here it goes, and if you want to pause the video and try it from start to finish on your own, then go ahead and do that. If you feel like you need to break it down step by step and press pause when need be, then go ahead and do that as well. So here's the question. It says, use bond dissociation energies to calculate the enthalpy change for the combustion of 1 mole of butane. So it makes sense that before I even begin, that I begin using my table of values for bond dissociation energies, that I take a look at what the entities are that are involved in this situation by writing out my reaction equation, and that's what I've done here. And so I always want to remember that writing out the entities doesn't tell me how many that I have, and I need to remember to balance this effectively. So just a brief note about that. In this particular question, they're saying that they want to know the enthalpy change for 1 mole of butane. So what I've chosen to do is to leave the coefficient of butane as 1, and to balance all of the other entities relative to that. And that means that at the end of the line, the delta H value that I get will be in terms of 1 mole of butane, which is ultimately what I'm looking for. So I've gone ahead and done that. Now, I mean, this is fine and good, this equation, but remember, in order to eventually solve the problem, I'm going to need to know how atoms are bonded within each of these molecules, right? Whether they're single bond, double bond, triple bond, and which atoms are actually connected in a covalent bond. So that's what I need to do next, is to draw out the proper Lewis structures for it. So I've gone ahead and done that. And so hopefully you remember from organic chemistry how to draw a butane molecule. And if not, that's okay. Here it is for you. But you can already see that I have a number of carbon-hydrogen bonds, but I also have some carbon-carbon bonds. And by drawing it out, I can see exactly how many of each of those are in one of those molecules. Now, in the case of butane, as it turns out, I actually only have 1 molecule, or 1 mole for that matter, because that's how I chose to balance this equation. However, in the case of oxygen, I only have 1 oxygen-oxygen double bond within that molecule, but I also have 13½ moles of oxygen molecules. So I need to take that into account in terms of when I'm adding up all of the types of bonds that are present in this situation. Okay, on my product side, I can also see that each carbon dioxide molecule has 2 carbon-oxygen double bonds. However, there are 4 CO2 molecules that are present. So it's almost like I could take this, let me go back for a minute. It's almost like I could take this CO2 molecule and rewrite it 3 more times, and that would tell me the number of CO bonds that are present. Okay. And in a similar way, I could say the same thing about water here. I can see that each water molecule has 2 OH single bonds, but because I have 5 water molecules, that's going to mean that I have 10 OH bonds in total. So I broke this down in the next slide. I find that in questions where it's a little bit more involved, there are a greater number of bonds and bond types, that it helps to sort of lay things out, sort of doing a bit of an accounting. So I know that if you take a look at your own drawing of butane, you'll see that if you count up, you have 10 carbon-hydrogen bonds, and you have 3 carbon-carbon bonds. And now I'm going to do the same thing for oxygen. But there's not much to do because I only have 1 bond in an O2 molecule, but I have 13 halves, or 7.5 O2 molecules. So there we go. Now let's examine my products. So I have 4 CO2 molecules, each having 2 CO bonds, as we discussed before. And there I have 5 molecules of water, but each water molecule has 2 OH bonds. So just outlining that will help to get me organized when I'm going through the next step, which is to calculate the final enthalpy change using all the different bond dissociation energies. So steps 3 and 4, you may remember, were to calculate the sum of the bond energies for the reactants and then the products. Now I broke that down in the first question, but it really can be done in one whole step together, as I'm going to show you here. So you'll remember that the total enthalpy of reaction is going to be the bond dissociation energy of the reactants minus that of the products. So here I've outlined the bond dissociation energy of my reactant. So you'll remember I have those 10 CH bonds and the 3 CC bonds from my butane. And then I've got 13 halves times that of my O2 molecule, that double bonded O2. Now I'm going to subtract that from that the sum of the bond dissociation energies from my products. Now there's a bit of a piece that I need to mention here, which is that in terms of carbon dioxide, you'll notice on your table that 799 is not the value that's in the table for a carbon-oxygen bond. On your table, it lists a CO bond as 745, and there's actually an asterisk there. So if you follow the table, if you look at the table at the very, very bottom of it, on the chart, it indicates that CO2, if the C double bond O bond happens to be in a CO2 molecule as opposed to another molecule with a C double bond O, then there's a special value for that's given for the bond dissociation energy. So again, in a molecule of carbon dioxide, the C double bond O bond dissociation energy is a little bit different than a C double bond O bond energy in any random other molecule, like for instance a ketone or an aldehyde. Okay, and of course over here I have 5 molecules of water with 2 OH bonds, and here's my bond dissociation energy for an OH bond. So if it might help for you to break this down, just so that you don't make any calculator errors, just doing each piece of this puzzle separately, and then finally ending up with a value of negative 2,178.5 kilojoules, and that's kilojoules per mole of butane. I have a negative value, which makes sense in the context of this question because I am combusting butane, so I'd expect there to be a significant amount of heat released from this system. So I hope that you found that question, this problem, fairly straightforward to go through. I know that it's a little bit tedious, but it is, I think, fairly simple. Just being aware of the details, making sure that you draw out those Lewis structures properly, and so that you're able to identify the types of atoms that are in bonds.